Perfect. Thank you for having me. Right before I came to San Francisco, I was at the VCAG meeting. So VCAG, the organization, right? MPEG and ISO ITU coming together to standardize the next generation video codec, VVC. And yeah, I want to talk a little bit about where that project is, where it's going, when it's going to be finished, what the current status is. And I want to do a little bit of a glimpse at the technical side as well. I'm an engineer. I've been working in codecs for a long time, and yeah, I want to show some of the cool new stuff that they're doing in VVC, which hasn't been done before. Yeah, the first thing about it, what is VVC? Is it a revolution or an evolution? In the scope of video codecs, well, it's more or less, it's an evolution of what has already been there. So it's still a hybrid video coding standard. It's based on HEVC, on a lot of the ideas behind it. It's refining a lot of the existing techniques to get more coding gain. But there are also a lot of new tools which are introduced which haven't been in video coding standards before. And yeah, I want to talk a little bit about that. Okay, first, let's start off with the timeline. Well, basically, right after the standardization of HEVC was finished, 2013, all of the companies which do video coding research and are contributing to the standardization in MPEG and so on did not close down their research labs. They kept on doing research and putting stuff into new software and trying things out. And so in October 2015, they started a new thing. So they formed the joint video exploration team to explore new possibilities in this direction. And basically, then in March 2017, a CFE was issued. This is how MPEG works in CFE and CFP. So CFE is the call for evidence. Basically, first MPEG says, okay, you want to start a new standardization activity, you want to standardize a new codec, show us that you have something which is better than what we have right now, so that it's worth it to start a new activity. The answer of that CFE was yes, it is. The software that they had was very performant, JEM basically, JEM-based software was tested, some variants of that, a lot of companies could contribute. So a CFP was issued, basically a call for proposals. So, okay, we want to start a new activity, what should we base it on? Please provide some software so we can get started. And yeah, the CFP was evaluated in April. There was a result and a common basis was established, and from that basis they are now standardizing a new standard. Also the name was established, versatile video coding, so it's meant to be very versatile. It's meant to address all of the all of the video coding needs, basically, from low resolutions, low bit rates, to high resolutions, high bit rates, HDR, 360 video, omnidirectional stuff, and so on. So it's meant to be very versatile. It's supposed to be finished in 2020, October. That's the planned date. And yeah, I want to present the current state of the standardization and what's going on there. So I want to start on, yeah, let's go a little bit into the technologies. What's in there? What's new? What's the new stuff in there? A lot of you might have heard about intra-prediction. Intra-prediction, the technology to, yeah, it's basically if you're predicting a block, you're using what you already have decoded in the same frame to do a prediction. There's definitely some evolutionary stuff going on here. So in HEVC, there were 33 directional intra-predictions. Now it's 65, so you can have more detailed prediction, a more precise prediction. In HEVC, only square blocks were predicted. Now they are also rectangular. I'm going to show another technology which is in there, which is corresponding to this later. There's larger blocks you can use for intra-prediction. There's new prediction modes where you can do a directional interpolation of the reference samples. There's now a chroma component prediction. So basically a chroma from Luma prediction. Some of you might have seen that in AV1. Similar idea. And there can be separate coding trees for Luma and chroma. So it's basically the logical next steps on top of what has been there for intra-prediction so far. Another evolutionary thing is what they have done in inter-prediction, so motion-compensated prediction, right? You're predicting a block based on reference frames, and you're copying the information from the reference frames to the current ones using motion vectors usually. There's also been some evolutionary stuff which has enhanced here. More advanced motion vector prediction, of course, so the prediction stuff has been enhanced. The derivation, but also there's a new mode where from a reference picture you not only inherit the motion vector over, but you also inherit the partitioning information. That's on the top right here. So for the blue block, for the current block, you not only copy over the motion vector that you have, like one of the motion vectors. That's how it's used to be in HEVC. But now you also copy how is that block split, and you copy all of the motion information over and do a better prediction using that. There's some ideas to do a combination of temporal and spatial prediction, and there's something else in there which has also been introduced in AV1 one now, overlap block motion compensation. Basically, you do for the current block on the bottom right, you do a prediction, and also for the blocks on the left and on the top, you do that. But you extend the borders of the top and the left block a little bit, and then you smooth everything together. Because what typically happens in motion compensation is you do two blocks, motion compensation, put it together, and then you will have a sharp edge between the blocks. Typical thing, because you copy it from different areas. And using this, you can have much smoother transitions between the blocks. Some more evolutionary stuff which has been going on. Of course, the arithmetic coding engine has also been enhanced, has been made faster, and has been adapted to the current coding schemes. For the transformations, there has been an enhancement. There used to be only one transform, DCT. Now they actually use 4 different transforms, 2 DCT, 2 DST, which you can signal in certain situations. The signaling is not fixed yet, but yeah, there's work going on there. But there's multiple transforms you can choose from. They are now separable, so you can also transform rectangular blocks, which is really cool. There's some advanced coding of those, and there's a dependent scalar quantization. That's a really cool idea, which would eat up like at least half an hour to explain. Really cool quantization enhancements to it. Really cool ideas there. Of course, the filters which are applied in loop are also being enhanced. Adaptive loop filtering is something which has been proposed in HEVC, didn't get in, and now, of course, they're back with the same idea. Yeah, some improved loop filtering. A palette coding mode is in there. That, of course, helps most for screen content coding. For screen content stuff, has also been in AV1, also has a mode for this. But now it's also in the VVC standard, or it's probably going to be it. As I said, it's not finished yet, but this is the current state of it. And there's some, now to the new stuff. What's really new in this? Okay, one of it is the block partitioning. You might know a video is split into blocks. Those blocks are split into smaller blocks, and then we do the prediction and transformation on these smaller blocks. How the picture is split, how the block is split, that is signaled in the bit stream. And there's now multiple splits which are embedded in a multiple tree structure. This is a really cool idea. There's basically 2 splitting stages after another. In the first stage, we do a quad tree split. So a block is split, like the example shows, a block is split, is either not split or split into 4 parts, into 4 square subparts. In the second step, we iterate over all of the smaller blocks that we have then and decide to either split them horizontally into 2 parts or vertically into 2 parts, or horizontally into 3 parts or vertically into 3 parts. And all of these steps, again, are embedded, so you can have a tree for those as well. And just to show a short example, so we have a block, now we decide to split it, we decide to split the top left again, we decide to split that one again using the quad tree. That is the quad tree split. This is it. This is the quad tree as we signal it. And now in the second tree, we decide how to apply the other steps. So for example, we decide to split that block horizontally. We decide to split that block vertically. We decide to split that one into 3 parts and that one as well. And now the whole thing is recursive again. So we can, for each subblock, we can decide again to split them. So we can decide to split that one horizontally again. We can decide to split that one into 3 parts again, and so on. You get the idea, right? It's all recursive, and that's the scheme how it's going. And something you can already see is the blocks, the resulting blocks, are no longer rectangular, or they are no longer square. In HEVC, there were also some rectangular blocks, but not so many, so it wasn't this flexible. Here you can actually have like 4 by 64 blocks. So you can actually have very, very small blocks. You can have rectangular blocks. You can have all different sizes, all different shapes of blocks. Highly flexible. Of course, this adds a lot of complexity at the encoder side. You have to test everything. Something else which is brand new, affine motion. It has been or AV1 has something similar or a similar idea, also using affine motion. Classical motion compensation only works on 2 dimensions, right? You have a motion vector and you copy a block as a prediction to the current one, but only 2-dimensionally. So you're just copying an array. You're copying an array of pixels to the current one. That's it. It's planar motion. That's it. And the idea of affine motion is to extend this motion, because in reality, not a lot of stuff moves plainly over the screen all the time. There's also other kinds of motion. There's also an object scales, an object moves and transforms. So it makes sense to map these more complex motions into the video codec as well. And so the idea is to extend the classical model, which is called 2DOF, 2 degrees of freedom, to more degrees of freedom to allow the block to move or to transform more freely. And there's actually 2 additional modes now. There's a 4DOF and 6DOF mode. And basically, the classical 2D one is, as I said, planar motion. You can move around a block. If you add 2 more degrees of freedom, so you add 4DOF, a block can also scale and rotate. And if you add 2 more degrees of freedom, then the block can also change shape and share, right? And so with that mode, of course, you have all degrees of freedom and all kinds of flexibility with motion prediction. Again, at the encoder side, this is very complex. You have to test all of this. You have to somehow search for all of it. But of course, you can more efficiently do a prediction. Okay. The way it is mapped into hardware is really cool, or the way it is mapped at the decoder side is really cool, because instead of doing it on a per pixel basis, which is very, very complex and very bad for hardware implementations, it's basically done on a 4x4 grid. So if we have a block, we signal 2 control point motion vectors, and then the actual prediction isn't done per pixel in the block, but for every 4x4 sub-block, which is already implemented in hardware. You just have to remap it and do a different signaling of it. And then if you have 3 degrees of freedom, you actually signal 3 control point motion vectors and calculate the sub-motion vectors using a formula and give it all to the hardware 4x4 reconstruction block, which already is in there. For example, in HEVC, there's a similar thing. Something other which is brand new, decoder side search. Yeah, it's a topic. It has been around for a long time. There have been proposals of this like 10 or 15 years ago. Basically, you shift some of the complexity from the encoder to the decoder. You say the decoder can also search for optimal motion in a picture, right? It has a lot of reference pictures. Why can't it search? And that's basically the idea here. Of course, that puts a lot of computational complexity at the decoder, but again, you gain a lot of coding efficiency. The idea is here, if you have normal by prediction, this is a very simplified thing. So for a current block, we have normal by prediction. So we're predicting from 2 references. We're copying the information from these references to the current block, do the interpolation, and then we have a prediction. And then using that prediction as a template, we search around the reference pictures which we already have for a better motion compensated block. And then we update those references, do the copy operation again, put it together, and then we have a better prediction for the current block. The search is pretty limited. It's basically right now, it's 8 positions around the block. That could be further extended, but as I said, it puts a lot of the computational complexity on the decoder, and yeah, it's a trade-off, right? It's a trade-off between how much more complex do you want the decoder to get, and how much are you willing to, how much coding gain do you want to have, or where's the trade-off, right? There's a trade-off in everything. There's, of course, a lot of tools which are still under discussion, right? Should they be in or not? There's a wide range of stuff. One of them is non-rectangular partitions, right? I said a block can always be split into multiple things, but it's always horizontal or vertical. Why not diagonal? Or in some other way, using a more flexible scheme? Why not? There's, of course, a lot of signaling problems, and how do you do things? It also extends your search range. But one of the things which is currently being discussed, I think it's actually in right now, let's see if it stays in, we don't know, is to also allow a block to be split on a diagonal basis, and then also do a smooth blending of the two predictions from the two references. Let's see if that stays in. We don't know. I mean, it's all still being discussed. There's also a lot of other proposals for this prediction stuff, like why can't you combine an intra-prediction with inter-prediction? That's also one of the ideas. Why can't you do a copy from neighboring areas within your current picture, right? Like intra-block copy. Of course, every time somebody proposes intra-block copy, the hardware guys will jump on stage and scratch their eyes out because they really don't like that. In hardware, this is really, really hard to do, and so yeah, they are definitely opposed to this. But yeah, let's see. They're discussing about this, right? A lot of other stuff. Secondary transforms. You can transform the transformed stuff again. It gives a little bit of gain. Is it worth it? Yeah. Motion compensation. There's a lot of fine motion models still being discussed. Local illumination compensation, right? What if the brightness of a block changes? You could signal a brightness change and just change the luma component's intensity with that. And the coding of everything, of course, is still under consideration or still being discussed. How do you reference pictures? What do you search on the decoder side? And of course, the high-level syntax is not set in stone at all. They're still discussing. For example, one of the basic questions is, are there going to be slices or tiles or both? Do we need this? What for? Right? It's a rather philosophical discussion going on right now. And of course, how do you reference the reference signal, the signaling of the reference pictures and all of that? It's there's a lot of work going on. They have 2 more years, so let's see what happens there. Then of course, what's most interesting, I guess, or to you as well, what's the current performance of this thing? First of all, I mean, this is the comparison of VTM2, so that's the VVC test model version 2, because this is the second iteration of it. Next, in 4 months, there's going to be VTM3 versus the HEVC HM reference encoder, similar configuration and so on. It's very preliminary, right? This is the second iteration. It's not finished at all. Not all tools which I have just talked about, which are already in the standard, so they decided to adopt them, are in the software yet. And the standardization is, of course, still ongoing. A lot of stuff is still being discussed, so this is definitely going to improve. This is not the end of it. And another point is that this is BD-PSNR, which is, of course, not the best subjective measure, and it has already been shown that on a subjective scale, VVC performs much better than HEVC. So the results there are even higher than the ones here. But what you can see, so there's a lot of different configurations that are being tested. For the random access configuration, which is the one we're most interested in, that's the one where you can use B-frames and prediction into all directions, so the most performant one. We currently are at 23% BD rate reduction compared to HEVC. So at the same quality, 23 or 1/4 less bit rate. And this is going to get more. I think the set goal is more like above 35 or something. So that's where they want to end, like 35 or 40. Let's see where it really goes to. You can't really say yet, but that's the set goal. At the same time, the decoder time doesn't increase that much, 120%, that's almost nothing. The encoder complexity also doesn't increase that much with this iteration of it, right? So far they are at around a factor of 4 compared to HM, which is, yeah, that's not that much, right, for the coding gain of 24%. And yeah, let's see if that increases or if they decide to adopt some more stuff which is more complex and will increase this. But yeah, let's see. There's discussion going on around this as well. Because just as a comparison, if you're comparing to the AV1 reference encoder, that would be more like that would be more like 2,000% or something. I mean, there's a whole different range to this. Then, of course, last but not least, I want to at least mention the licensing situation. Of course, the licensing situation for VVC is unknown. VVC is not finished yet, so yeah, you don't know anything. No company has published anything on that yet. But what we do know is there's going to be a license for this. This is not an open source standard. This is not meant to be freely used for everybody. This is meant to make money. This is meant to be licensed by people. One of the problems, I mean, we all know the problems which came up with HEVC. 5 years after it has been finished, there's still not one licensing model to pay for HEVC, which is, of course, yeah, a weird situation to be in. The problem is that JVET, so the joint team doing the standardization here, is a technical team, and they are not directly responsible for this. They can't say, we will not adopt your proposal because you behaved badly in the past. They are a technical team, they are not allowed to do this. So the parent bodies would have to change the licensing agreement to somehow push out companies, and the problem is that that has to be done at a global level, right? They're global organizations, so they would have to have agreement on that on a global level, and that's very, very complicated. It's politics. I'm not really, I don't know that much about that. What happened so far is that the Media Coding Industry Forum was formed. So basically a lot of companies came together and said, yeah, we have to do something about it or talk about this and see if we maybe not be able to improve the situation a little bit. That's basically all it can do. It also has no real power over anybody. Yeah, but it's a first step. Some step has to be taken. Yeah. I'm not going to do a prediction on what's going to happen on the licensing situation. I'm an engineer. I'm going to say there is a possibility that it will end up at a similar situation as HEVC, or maybe the companies learn from this and yeah, it's going to something usable is going to come out of this. Let's see. Okay, some references, and then thank you so much for your attention. If you have any questions, please come out and ask me. If you want to talk more codecs, tonight I think we have another event at the office. Come by, grab a card, and yeah, then we can talk more codecs and more stuff. Thank you.